Welcome to the new quantum era. I'm your host, Sebastian Hassinger. One of the recurring themes on this show has been the question of when quantum computers will actually be useful for science. Not in the abstract, someday we'll simulate molecules way, but in the concrete sense of producing results that a working scientist can trust and use. We've had recently Dominic Heinleiter speaking about quantum advantage, but more further back, we had Martin Savage talking about simulating high energy physics. And across the literature, the honest answer has mostly been not yet, but we're getting closer. Today's conversation moves the needle in a meaningful way. Arnab Banerjee is an experimental physicist at Purdue University and a guest scientist at the Quantum Science Center at Oak Ridge National Laboratory. He's a rare person who both grows exotic magnetic crystals in a lab and then takes them to the billion-dollar neutron scattering facilities at Oak Ridge to study what their quantum states are actually doing. His 2016 Nature Materials paper provided the first experimental evidence for Kitaev quantum spin liquid behavior, a phase of matter that could, in principle, host the kind of topological excitations that would make qubits naturally resistant to errors. That paper was Discover Magazine's number 18 story of the year. But what brings Arnab on the show today is something different. About 10 days before we recorded this, he and his team published a paper with IBM, Oak Ridge, and Los Alamos showing that a 153 qubit quantum computer, IBM's Heron processor, can quantitatively reproduce real neutron scattering data from a magnetic crystal called KCuF3. Not approximately, not qualitatively, the quantum simulation matched the experimental fingerprint, the spin-on excitation spectrum, well enough that Alan Shea at Los Alamos called it the most impressive match I've seen between experimental data and qubit simulation. KCuF3 is a fluorinated perovskite compound known for its unique magnetic and electronic properties, including being an orbitally ordered wide band gap insulator. It consists of potassium, copper, and fluorine, and exhibits quasi-one-dimensional magnetic behavior. Now, an important caveat, KCuF3 is a one-dimensional system. It's well understood classically. This is not quantum advantage. Arnab says so himself. It's a benchmark. But it's the kind of benchmark that matters, because if you can't reproduce a known answer, then you have no business tackling the unknown ones. And Arnab has decades of neutron scattering data on materials where classical methods genuinely fail. Frustrated magnets, two-dimensional spin liquids, systems where entanglement spreads so fast that no classical simulation can keep up. That's where this is headed. What I find especially compelling about Arnab is that he's worked across essentially every quantum computing modality. IBM's superconducting gates, QuEra's neutral atom arrays, G-Wave's quantum annealing, and he has a practitioner's view of which platform fits which problem. It's not tribal, it's pragmatic, and that perspective is rare. Before we get into it, this episode, again, is brought to you by Qubits OK, a dedicated job board and research digest for quantum computing. If you're building a career in quantum or hiring for one, this is the signal in the noise. Every week, they send curated job alerts filtered by over 400 specialized quantum tags, trapped ions, QEC, quantum ML, you name it. They also run a daily archive digest that surfaces the papers that actually matter to your specific research interests. I use the daily digest myself. It's one of the tools I rely on to find my next guest for the show. It's free to subscribe. Head to qubitsok.com and sign up in 30 seconds. And if you're hiring in quantum, use the code NewQuantumEra-50 for 50% off your first job posting. That's qubitsok.com, code NewQuantumEra-50. Here's my conversation with Arnab Banerjee. Hi, Arnab. Thank you very much for joining me.
Thank you. It's my pleasure to join you here.
Yeah, it's good to see you again. You've got a really interesting story. So before we jump into the current research, the current topic that I want to talk about, can you share a little bit about your path to Purdue and the Quantum Science Center? How you got to where you are today?
Absolutely. So, I am an experimentalist in my DNA. So, I do experiments. I grow materials and then I go and measure them using cutting edge techniques, which includes neutron scattering, which includes transport, which includes X ray scattering in many of the national laboratory facilities. So, the way I got here is that I was. I did my PhD at University of Chicago with Tom Rosenbaum, who right now, by the way, is the president at Caltech. And he was a really big proponent of quantum computing himself back in the days, back in 2000s. And with him, I did work on classical and quantum phase transitions in magnetic materials, but also got interested in magnetic materials and what kind of magnetic materials could really become tomorrow's quantum materials for applications, for computing, for sensors. And that research really took me into Oak Ridge National Lab, where I was a postdoc. I worked on developing and discovering a new kind of a quantum spin liquid material called called the Kitaev quantum spin liquid material, and I took a lot of neutron data on that. And what I figured out is that the community really lacked a good understanding of how to deal with such complex data sets. Things are quantum, but they are using classical tools and classical approximations. And because of this dichotomy, this problem never gets truly solved. And when the problem never gets truly solved, you can't really develop anymore. So that is what got me into quantum computing, because I thought that that would be the way in which we can solve these problems. And it was that frustration or that pain point which got me into quantum computing in the first place. And then I started working in Oak Ridge National Lab with folks like Travis Humble in their Quantum Computing Institute, and started learning more and more about how can we actually use quantum computers to get access to real data sets. And then I came to Purdue partly because I think that it has a great quantum computing environment. Microsoft QStation is here. They also have great national lab partnerships, and I can actually develop this with students, which also makes the next generation come up. And then one thing led to the other. I think that we started working with many companies, and now we are here. So I do experiments and try to get data which we could possibly explain with quantum computers. And that was
Right,
my
right.
brief history.
Yeah. So you call yourself an experimentalist through and through, and I think I saw a quote from you, and I actually think I've heard you say something like this, using words something like this, like making uncertainty your friend. Is that sort of like how you see the challenge of experimentalism? I guess in physics. So you mentioned Kitaev. That's the theoretical work that you have been sort of trying to like experimentally test and like prove out essentially, right? The topological states of matter.
Correct. So, yes, I think that almost the entire electronic industry is built around trying to avoid quantum effects as much as possible. And I think that this is the time when we need to basically make quantum our friend instead of our enemy, and fundamentally change the way we can actually miniaturize things and get across that barrier into a new kind of Moore's law, which would be over encompassing quantum. And which means that we need to rethink the way we design electronics. We need to rethink the way we design any circuitry. And one of the things that we thought, which is what attracted me to the Kitaev magnetism, is because Kitaev gave this theoretical framework of how to make a quantum computer or quantum gates, which are naturally protected from decoherence. As you know, decoherence is a big problem. And they are naturally protected from decoherence by nature. So there are materials where nature works in a way that they are naturally protected. And if you can actually take some of these materials or build some of these materials out and make circuits out of that, then you are already setting yourself up for advantage. Not only that, a material platform is ultimately the most scalable platform, as we know from the semiconductor boom. The reason I got very interested in that research, and I'm still very interested, is because I think that that's one pathway we can get to truly protected qubits, which are scalable to the billions one day. And yeah,
That's really interesting. And so that pursuit of topological states, of exploring topological states, led you into this decade-long set of experiments, I would say, right? And for people who, like myself, are not condensed matter physicists, you mentioned quantum spin liquid as one of the things that you have discovered through your experimentation. What is a quantum spin liquid?
A quantum spin
In
liquid.
simple terms, no
No,
problem, right, Arnab?
no, absolutely no problem. Because I've been asked this. So, think of a normal liquid like water. In water, what happens is that all the molecules are randomly moving around because of something called Brownian motion. There seems to be like no rhyme or rhythm. On the other hand, on a surface of water, you go and throw a stone, you form ripples. You form this nice vortices, and which means that there is an overall orderliness in the way the molecules collectively move, although individual molecules are all moving around like random. That is exactly what you have in a quantum spin liquid, where the spin directions basically move collectively in ways where they make these really nice dancing patterns, which look extremely ordered. But although the spins themselves, if you take a snapshot, feel that they are all completely random. And from that orderly motions, essentially new kinds of particles can emerge, new kinds of statistics can emerge. And some of these statistics are topological. Some of these statistics have very interesting patterns. Just like in water, you see vortices. When a ship goes, you see this nice vortices form, and these vortices are really long-lived. That's a really interesting example of a topological state in water, in a liquid water. And that's exactly the same kind of a state that you can have in a spin system where these vortices become really long-lived in a quantum spin liquid. And if you can encode your information in that, that becomes really long-lived and protected.
Right. So intuitively, it sounds like it. What you're saying is almost the analogy here is the topological system is like a vortex in the water, which has staying power, even in the random chaos of the individual molecules of movement of water. The vortex itself has its own. The spin itself has momentum. It has an actual sort of almost lifespan, while the energy of that vortex runs down. So, when you say those are observable, do you mean in sort of like the ground state of a condensed matter, like a crystalline structure or lattice or whatever? Is that what you're observing?
Yes. So you will need to look at. So there is the electronic ground state, and beneath the electronic ground state, we have the spin ground state. So once you look at the spin ground state, then you get a very clear signature of these motions. And that's what we are on.
Interesting. And so you mentioned in one of your tools in experimentation was neutron diffusion, and using and using the Oak Ridge spallation facility. Is that right? They've
That's
got that.
right.
So how does that work as a tool in your experimentation?
So it's extremely interesting, and I can speak days about it. So literally, the way a neutron is produced is by having some kind of a material like tungsten or mercury, which has a lot of neutrons. It's a heavy metal, and then bombarding it with very fast protons. And that proton, when it hits this metal, it basically gives out a burst of neutrons. What you do is that you slow those neutrons down and then you put them in a tube like a waveguide, and then you make them project onto a certain material of your choice, which you are trying to study. Neutrons have three very interesting properties that makes it useful. The first property is that the neutrons, they have a mass, which means that they have something called a de Broglie wavelength in quantum physics terms. In other words, it behaves both like a wave and a particle at the same time. And the wave nature of that neutron means that if it hits a material, it will diffract. And on the screen, it will produce a pattern that essentially gives you the information of where your atoms are. Not only that, if you can figure out how much energy this neutron has lost, it will also tell you what are the allowed energy levels in the system, which means that it will tell you how these atoms are actually moving. So it gives two information at the same time. Now it gets even better. Neutrons not only have a de Broglie wavelength, they also have a spin. So they are spin half particles, which means that the spins of neutrons will directly interact with the spins of your material, and it produces some of the cleanest data of spectroscopy that you can ever get in a magnetic material. And that is what we really rely to figure out what the material is really doing. All the spectroscopic levels completely separated out in energy and momentum. And so it's an extremely powerful technique. And since it works as a weak scatterer, you can do an exact theory on the result which comes out. And neutrons have a lot more interesting properties. I mean, it also gets absorbed. It penetrates the material depending on its the content of its nucleus. So you can do imaging with neutrons. You can do fracture imaging with neutrons very nicely. Something which is done quite a bit in Los Alamos National Laboratory. Here we are using it to, in our research, we are really using it to do a momentum result spectroscopy. And there are very few techniques that can do that so cleanly. And neutron scattering is clearly one of the winners in that technique space.
Interesting. So, this one of the motivations for this line of experimentation, as you said, was sort of trying to improve the materials that are used for building qubits, for fabricating qubits, try to make something that will have more resistance to errors because of topological states, greater coherence times, those sorts of things. But now actually since we met, you've been exploring the use of quantum computers to simulate materials. So what's the role, when you have that neutron scattering technique, what's the role of quantum computing simulation in the material science experimentation that you're doing?
Mostly, there is a twofold requirement. The first thing is that there are no competent classical techniques as we scale up in size and scale up in number of dimensions, which means that you only have approximate classical techniques or no classical techniques. And then if you have really nice data and nothing to analyze that data with, then that's failed science in some way. I mean, and I think that that's what quantum computing can really solve, is make that connection right away, and then it can predict.
Nature isn't classical, as Feynman said.
Exactly, nature isn't classical, and since nature isn't classical, we need a quantum tool to solve a quantum problem. And and uh, and as we see that, then we can go and ask these questions, which we cannot ask right now very well, by the way, because we cannot solve things. We can start asking these questions that, okay, now we know what the system is really doing. Can we see what is happening microscopically? Can we look at can we perturb the Hamiltonian? Can we actually see if this could be a good sensor? Can be a good qubit? Can it be a good information carrying bus from one place to the other? And all those questions we can only ask when we understand the material better. And that's what I think it really
That's great.
yields.
That's great. And so this recent work, I think, was just published to the archive about 10 days ago at the time of this recording. It's a collaboration with Oak Ridge, with Los Alamos, with IBM. And essentially, if I'm correct, you're using the Heron chip, or about 50 qubits on the Heron chip. I think the Heron's 150 something.
Yeah.
To essentially simulate or neutron scattering data and see if you can simulate it accurately enough to match your actual experimental results from real neutron scattering. Is that right?
Exactly. And this is one
Yeah.
step we absolutely need to do before we tackle more complex,
Of course. Yeah.
more complex neutron scattering data.
You have to have a reference point to prove that your simulation actually is valid before you take off into the realm where you can't actually simulate it classically or validate it. Yeah.
Exactly.
Interesting.
We need to know whether what we are doing really makes sense. And that's what this experiment is about.
Yeah. So walk me through the details of what was the experimental data you had, and how did you simulate that on the IBM system?
So the experimental data was partly obtained at Rutherford Appleton Lab, fondly called ISIS, by the way. That's in United Kingdom, and then partly it was obtained at Oak Ridge National Lab, and then it was stitched together. And many of these works were happening over quite some time. In fact, this is a very well-studied material, and there is this groups of Alan Ten and Steve Nagler who had been working on this material for a long time. And turns out that this is a really nice Heisenberg spin chain, which almost complies nicely with a Bethe-Ansatz solution named after Hans Bethe, who first proposed its solution exactly. And it does produce a type of a quantum spin liquid in one dimension, which is very akin to something called a Lottinger liquid, which now that's a lot of jargons, but overall, it's a really nice problem, and it's a problem which gives us the confidence that, look, we are getting interesting quantum states out that we see in a real material, but now we also see it in a quantum computer, so that we can make a one-to-one benchmark. And so, and this material basically shows these really nice quasi-particles called spin-ons, which basically are fractional. What that means is that it is as if the electron has broken apart into fractions of itself, which is not possible normally, but in a quasi-particle sense, in a many-body system, that is effectively true. So you see these very interesting properties, and we thought that this would be the material that would convince us that we are ready to tackle complex problems. At least let's show that in one dimension. In one dimension, of course, we are not talking about quantum supremacy per se, but it is a great benchmark problem.
Yeah. And I'm curious the reason for selecting the particular experiment to test your simulation on the IBM system. The reason for choosing something that had the spin spin liquid systems, is that because that's it's a good workout for your simulation, for your circuit. It's a good challenge to sort of stretch, or is it because of your pursuit of spin liquids as a potential key for unlocking better materials for quantum computing, or both?
I think that it is the first one in this case, because because you want to see that your quantum computer is giving you emergent states. Emergent states are states where you have collective excitations. These are states which do not natively exist in the two-body interaction in the qubits, but can emerge effectively as you evolve the system. That's when you know that yes, I mean all the spins are doing or all the qubits are doing all its random things, but at the end it's giving you something which is more than the sum of its parts. And this is one problem which helps us benchmark that. And that is what guided us to this problem. And turns out that many of these type of problems are spin liquid problems, we like it or not, of different kinds. And and there are non-spin liquid varieties of these problems as well. But this is a problem space where we have really nice data, and we trust that data. We can benchmark it not only against theory but also against experiments. And so that's what really got us into it. But yeah, I mean, we have still not gotten to the types of materials or Hamiltonians that would give us a true quantum advantage or could help us make qubits or sensors or anything. But that's the, yeah.
And that when you refer to a quantum advantage, do you, in your mind, is that by definition a topological qubit, a Majorana fermion sort of based qubit, or do you think spin liquids may afford other advantages in the characteristics of the materials, longer coherence times, or other means of providing a better foundation for fabricating qubits?
It may. So this is basically research that some of it will still need to be done. There are actually frameworks for quantum spin liquid based qubits. One of them was just published in Physical Review X by Jason Alicia from Caltech. So there are frameworks for that. Now, the engineering towards that will now need to catch up, of course. And
As is always the case.
as is always the case, and and what I am hoping is that we also need to understand not only the engineering, we also need to have enough confidence on the materials to pour in, let's say, a couple of $100 million on that research so that it develops. And I think that what the quantum computing research can help is to provide that level of confidence, that modicum of confidence that actually brings in that funding into the space to develop these new systems. But having said that, Majorana qubits, as you know, are being pursued by Microsoft with varying degree of success, and and uh, protected qubits are being pursued by everybody, by Continuum, by Google. All of these are actually some type of a surface code, some kind of a topological code which they are employing.
Right. That is fascinating to me, that surface code is just a logical set of operations that are, in a sense, simulating a topological state of matter.
Exactly.
And potentially you could achieve a topological state of matter to instantiate a qubit physically and have that protected logic sort of embedded in the design, essentially, of the material, and then the qubit that's realized in the material.
Exactly.
It's so fascinating. I love that feedback loop of quantum computers helping with quantum physics experimentation and research, which then helps making better quantum computers. When we first met, you were doing a simulation in collaboration with QuEra on the Aquila device. It was a Shastri-Sutherland material simulation. You've done work with the D-Wave quantum annealing system as well. Now you're working with IBM's system. Do you see sort of the modalities as all having different roles to play at this stage in the experimentation?
This is actually a very important question, and I have been asked by many people. And actually, I am one of the groups who has worked with many of these modalities. And each backend each modality has its advantages and disadvantages. I'll give you an example. IBM has qubits which are extremely fast. They are transpond based, programmable, and but they have a 2D lattice. For the research that we are doing, it actually requires many quick, cheap qubits. So that's a bit fantastic. That's operation. So that's fantastic for the research. So that's a great fit. Something like Continuum, for example, has a much more all-to-all connectivity, but they are slower. So if somebody really needs that all-to-all connection for some kind of a Hamiltonian, then they will better be using that. On the other hand, if somebody says that, oh, I don't need so much of programmability of X, X, Y, I don't need to measure in X, Y, Z, all kinds of bases, Heisenberg is not required. I only need an effective model which is Ising-like, and a transverse field Ising is gonna make good for me. Then I think that D-Wave and QuEra will, depending on how quantum you need to be in the overall scale and how quick you need to be, I think that they offer better products. So it really depends on the problem that we are trying to solve, and we really need to fit the backend modality to the problem. And this is where I think the success can really happen.
That's really interesting. You've written a roadmap paper on materials for quantum technologies. What do you think the pipeline looks like from your perspective, having done these experiments on a variety of different modalities and being very close, to obviously coming from the physical experimentation and now doing simulation? How far are we from discovering or improving materials for direct use in the design and fabrication of qubits, do you think?
So I think that as far as quantum helping is concerned, we are actually quite close. I'm actually monitoring this space of going into error-corrected qubits or error-corrected logical qubits. I mean, I am both optimistic and cautious at the same time, because
Of course.
optimistic because it'll probably be better qubits, but cautious because the effective number of qubits will shrink, and the effective kind of operations that you can do with those qubits will also probably change. So I think that the trajectory of this research is going to change over the next 2-3 years as we go into that space, and it will be interesting to see where we land at the other side of it. Having said that, I think that the goal is to basically make sure that maybe 70 or 80 or 90 qubits in some kind of a 2D geometry is coherently coupled for an amount of time which is probably like j by 20, where j is 20 by j, where j is the interaction scale. And then we are already getting into a point where there are classical techniques that will not be able to do it. So from that standpoint, I think that we are just a factor of 2 off.
Right. And sorry, do you mean 70 to 90 qubits, logical qubits that are fully protected with surface code, or do you mean sort of good enough qubits with enough
qubits.
connectivity?
Good enough qubits.
So maybe error mitigation or high enough fidelity for the 2 qubit gates and enough connectivity.
Correct.
Yeah.
And from that standpoint,
that's not that far off.
Yeah. Exactly.
That's interesting.
Yeah.
That's really interesting.
The choice of problems would be important, though, and
of course,
in that space.
Yeah, I mean, I think that's where your set of experiences becomes really, really crucial, because you can draw on your experimental experience and tailor the experiment to the characteristics of that system to choose a problem that is not classically accessible, but is accessible to that particular system's architecture and characteristics. So that's really exciting. And so, okay, last question. With the years of physical experimentation with neutron scattering, if we, forget about 70 to 90 good enough qubits. If you say, okay, you've got a quantum computer of arbitrary quality and scale, what's the material science or the neutron scattering problem you would throw that system at first? What's the answer you want to get overall?
Well, there are quite so many, but I think that I would like to simulate. I would like to simulate the entire standard model using a quantum computer. Get everything.
That's a modest goal, yeah.
Theory of everything with that.
Yeah, a theory of everything. Okay, yeah. I think you're not alone in that. I think that's what everybody. So that would be from the perspective of starting with material science and building up, essentially, right?
Right. I mean, more realistically, I think that there are problems which are completely untractable using classical computers that we can tackle. I mean, the frustrated triangular lattice. It's so simple to think about it, but it's so inaccessible. And any model where you have more connectivity, the more the connectivity you have, the quantum entanglement kind of spreads so fast that you are completely clueless about what is happening after a certain amount of time. And any of these problems become quite accessible. Understanding what's the interaction between spins and electrons. It's mostly a problem which many theorists don't want to touch, and I think that those will start getting accessible, and we will get a much better understanding of what's going on around us.
Mm-hmm. That's great, Arnab. I mean, I think, like I said, I think your set of experiences makes you the type of person who's uniquely able to navigate this emerging space. As we get closer and closer to being able to tackle classically intractable problems. I think I'll be watching you because I think you're going to be among the first to get to those really interesting results. So yet another really nice piece of work. I'm always quite impressed with the work you're doing. So thank you so much for joining me today.
Thank you. It was my pleasure.
Thanks to Arnab for that conversation. I love the clarity of his approach. Start with what you can verify, prove the quantum simulation matches reality, and then go after the problems that classical computers can't touch. The fact that he's done this across IBM, QuEra, and D-Wave hardware, matching the modality to the problem each time, is a model for how this field should work. If you want to dig deeper, the March 2026 benchmarking paper, the original Kitaev spin liquid work in Nature Materials, and the Materials for Quantum Technologies roadmap are all linked in the show notes, along with Arnab's lab page at Purdue and the Quantum Science Center at Oak Ridge. This episode was brought to you by qubitsok.com, the dedicated job board and archive research digest for quantum computing. If you're looking for your next role in quantum or you're hiring, Qubits OK filters by over 400 specialized tags, so you're only seeing what's relevant. Free to subscribe at qubitsok.com, and if you're posting a job, use code NEWQuantumEra-50 for 50% off your first listing. That's qubitsok.com, code NEWQuantumEra-50. If you want to go deeper on the topics we cover, research highlights, commentary, and the occasional behind-the-scenes look at what's coming up for the show, sign up for the newsletter at newquantumera.com. It's free and is the best way to stay in the loop. And if you have an idea for a guest, a topic you'd like us to dig into, or just want to say hello, reach out through the website. I read everything. If you're enjoying the show, please subscribe wherever you listen to podcasts and leave a rating or review. It genuinely helps new listeners find us. If you know someone who'd appreciate a conversation about the real science behind quantum computing, not the hype, the actual experiments, send them this episode. Thanks for listening. I'm Sebastian Hasinger, and this has been The New Quantum Era. Theme music by OCH. See you next time.